we'll start from there. Okay. So this chapter talk about system protection. When it comes to the power system protection, guys, there are multiple protections that you can provide for the system. One of them is overcurrent protection device. If the current go above a predetermined value, you need the circuit breakers to trip before you burn your equipment. If you have a short circuit, you need the circuit breaker to trip before you burn equipment. That's what we call an overcurrent protection device. Nothing new to you. What I'm going to emphasize is a couple of coordination here you're going to see in a second, and different type of overcurrent protection devices. Overcurrent protection, guys, is not the only protection for the system. If you are lucky enough in your life, you probably do high voltage like Brian is doing. For Excel, you could be a relay engineer and you would do over under frequency, over under voltage protection, over under frequency protection, over under voltage protection. You can do directional overcurrent protection device, differential relaying, tons and tons of protection, guys, that you provide for the system. Single phasing. Most of us get involved, a lot of you guys get involved in the most notoriously famous protection for any power system is overcurrent, because it burns the equipment. So that's what we're going to be talking about today. A couple of things: identify devices used to protect system, overcurrent protection device, and that will be the systems that we use for protection is circuit breakers and ground faults and fuses. How does the circuit breaker and the fuse and the ground fault protective devices, these are the one, two, and three devices notoriously famous when it comes to overcurrent protection device. Either you put a fuse or a circuit breaker, right? Or you put a circuit breaker with a function that's have ground fault protection. We'll talk about this one in a second. Proper adjustment of these devices with adjustable element. How do you adjust the overcurrent protection device? You guys, not next week, I believe next week or the week after, we're going to be doing SKM power system analysis. You're going to see adjustable circuit breaker in this 4,000 amp switchgear, and you're going to adjust the overcurrent protection device, long time pickup, short time pickup, instantaneous pickup, as well as the delay. So there's a lot of delay on them. Selective coordination. Selective coordination, we talked about this one before, guys. It's if you have a short circuit if you have a short circuit or a ground fault right in any of these pictures above your head, do you want the circuit breaker in this panel to trip, or the main, the 1200 amp main done with it to trip? Obviously, you want this one. That's called selective coordination. And we'll talk about, show you a couple of curves. Okay, a ground fault protection, guys. First, you can have, like I said, there's when you protect any system, you have a circuit breaker or you have a fuse disconnect. And here's a panel, any system, right? And with this, there's something called ground fault protection, or also a function that they use it here with a relay, ground fault protection. So ground fault protection, so we know what a circuit breaker does, right? If you if the circuit breaker is rated for 200 amp and you pull 220, it takes a couple of minutes, it trips. If it's 200 amp and you have a short circuit, a 2000 amp, it will trip instantaneously. Fuse is the same way, guys. For systems too large, 1000 amp or more, 480/277 systems, volt, solidly grounded, the code require you to have a ground fault protection. These are sensors specifically looking at the current that's going to the ground. The reason why they do this, guys, a lot of people get confused with this type of protection. The reason why they do a ground fault protection on a system as high as 1000 amp, because take the 4000 amp switchgear that we have. If you have a short circuit 3000 amp, do you think the 4000 amps will be able to see it? No way. You know what? 3000 amp short circuit that can burn the building, ground fault. So the smarter than Chad, long time ago, discovered that if you have you need another protection that's called ground fault protection. It looks at the three phases, the current in each phase, in the neutral, calculate them, and if the difference is substantial, this means you have a ground fault somewhere in the system. It alarms and or trips. It alarms and all trips. Any comments, guys, about the ground fault protection? Specifically, the condition for the ground fault protection is very clear. You have 1000 amp and a system of 288/277. So is it required in 288/120? No. 240/120? No. Is it required at 480 delta? No. It's always grounded. That's basically a system or 600, 370 something. So that's the only place that's required by the code. Any comments, any questions? Required on the feeders as well as service and soon to be branch circuits. Okay, so that's required. Recommended, like I said, it's required on the service and the branch circuit on the feeders. Recommended, guys, and soon to be required on the branch circuit soon, and on all other feeders. Less than 1,000 amp. Again, it's recommended by engineers. When you go work from Shunt Erickson, guys, you're going to find, or Parson, Darren, my friend, you might find them having a ground fault protection on a 225 amp panel. That's okay, recommended. Required only in 2 locations, feeders and branch circuits, anything 1,000 amp or higher, 480, 277 to ground. That's where it's required. Recommended in all the systems. In any system, probably I would say start making sense at maybe a 600 amp or more. Okay. Not required in any area that tripping will create a hazard. Not required in any area where tripping create a hazard. So if you're cooking nuke or cooking chemicals, you don't want to wear ground fault protection because you could trip and increase more hazard. Does that make sense, guys? In any area, that will cover all chemical, sensitive chemical and manufacturing equipment that you cannot interrupt because of a ground fault trap. I don't care if there's a ground fault trap. In interrupting the process will create more hazard than having a ground fault. Does that make sense? Industrial applications. Okay, so that's selective overcurrent protection device. When we say selective overcurrent protection device, guys, if you have a short circuit right here or ground fault right in this location, the one that's going to trip is this one, not this one, not this one. Okay? Does that make sense, guys? You have a short circuit right in this area. The one that's going to trip is this particular circuit breaker. That 25 amp or 15 amp circuit breaker. Any comments, any questions? Because what happened if this one trips here? You lost all the panel here, and you lost all the panel here. So that's what the whole coordination, overcompression coordination is. Here's the ground how the ground fault protection works. You have a current that's going on each one of these pairs, 1,000 amp, 1,000 amp, 1,000 amp, and returning on the neutral is 0 amp, for example. It calculates, that's a balanced system, everything is okay, calculate the current coming in, coming out. If there's a ground fault in one of these phases, so some of the current here will go, let's just say that ground fault was 500 amp. Look at this, 500 amp. So you have a ground fault 500 amp right in this phase. So the current that continue here is what now? It's 500 amp. What happened to the other 500 amp? It splits. 500 amp went back and another 500 amp went to the ground fault. Can you guys see now the system is unbalanced? If you do the math, there will be an I neutral current here going because it's unbalanced, substantially unbalanced, right? And this device, CT, will look. The minute they see something like this, it will create a 5 amp current that goes to a little coil here, and that little coil energizes and bam, trips the circuit breaker. Why it's so important to have this ground fault protection? Because at higher amps, like 1,000 amp or higher, guys, a ground fault can be as high as 1,000 amp, but it can't be detected. So this is only required on 1,000 amp, like we said, 480/277, the volt, the amp, and grounded system, grounded system. So that's where it's required. Recommended in a lot of other systems, especially that's grounded. Any comments? Feeders and branch circuits. This is also feeders, and I'm sorry, service entrance. Feeders and service entrance conductors. And Jeff, to be ahead of the curve, in 2014, they're requiring it also on a branch circuit. So if I have a load, an air handling unit, that's 1,000 amp or more, you have to have a ground fault protection now. Any comments, guys? Any questions about that? In hospitals, they require you to have 2 levels, at least 2 levels. Here, they have 1 level. A lot of engineers can have multiple levels, guys. When they have a ground fault, they have one ground fault here. A lot of engineering firms, one ground fault here and one here, down to the equipment. So this will be ground fault protection 1, ground fault protection number 2, and ground fault protection number 3, and these will be coordinated. I'll show you in a second how they coordinate. Any comments, any questions, guys, about the ground fault? Comments, questions? So that's basically your ground fault. Okay, now we'll get back into a couple of diagrams, guys. Circuit breakers. Talking about circuit breakers, you guys are familiar with the air circuit breakers. Right here, they're in this panel. There are 3 types of circuit breakers. There's the air, and there's the oil, and the vacuum. These oil and vacuum, guys, mostly medium voltage and high voltage. This is Brian. That's what Excel does. Oil and vacuum, mostly. Oil and vacuum for medium voltage and high voltage circuit breakers. A lot of us, most of you, if you're working for the building, you're dealing with air circuit breakers. That will be from 15 amp all the way to 6,000 amp. Air circuit breakers, and the voltage is 600 volt. 600 volt. That's what basically you're dealing here is, right? That one is called air circuit breakers, meaning when you interrupt the short circuit, you interrupt it in the air. There's no oil where the contacts are immersed in the oil, or there's no vacuum where they have a vacuum tube. There's no air at all in it. Okay, so that's basically 3 types. Thermal circuit breakers send circuit through protection of heat. Then there's, so the types, the structure is 3 types. Then the sensing mechanism is also, guys, 2 types, 2 or 3 types, how they sense to trap. Thermomagnetic. Thermal, remember that thermal, it sends thermal, it expands to dissimilar materials, expands at different rates, it trips the circuit breakers, that's a thermal. The magnetic, a coil, you energize a coil, a short circuit happens, and bam, it pushes, literally pushes a contact to open. And the last one, guys, is electronic. Electronic is you have a sensor, a CT that senses the current that goes through the conductor, make a decision is through electronic devices, and trip the circuit breakers. So thermal, so this is just a few things about the thermal circuit breakers. It has some heaters. The bimetallic is stripped. There's some delay exposed in it, delay before the circuit, depends on the amount of current. And here's how we look at this one. Here's how this works, guys. The current goes, if this circuit, this is my load, if this circuit is supposed to protect you, if this is a 15 amp circuit breaker, and now we're pulling out of that boy a 20 amp. Look what happened. You're pulling a 20 amp out of 15 amp circuit breaker. This heater starts creating more heat. As the heat start coming out, guys, here it heats this material. When this material heats at different rate, it will move. Can you guys see that contact? It will move that little deal here, and it pushes the contact to open. When you contact open, it interrupts the flow of that 20 amps that's going through the circuit. So 3 heating, 2 dissimilar materials. That's called the overload. That's very similar. That function is the overload, protecting from overload. Any comments, guys? Any questions about that? Very easy, very similar, right? Now the second component, this is how they represent it. This is basically my overload condition. So the circuit breaker is providing overload. The second part is magnetic. Magnetic has a coil, energize the coil, create a magnetic field, bam, slam these contacts open. So sense the current by connecting a coil in series. This is called instantaneous circuit breaker, part of the instantaneous. Thermal circuit breakers employ. Now then, the most of the circuit breaker has the 2 together, guys. They call it thermomagnetic circuit breakers. Have a thermal component and a magnetic component. Okay, here's your thermal. Here's your magnetic. Suppose I have my 15 amp circuit. Now I have a short circuit here. I went here and I shorted here to ground, right? So what happened here? I'm pulling, instead of 15, I'm pulling 150 amp. Is that a short circuit? 10 times? That's not a short circuit. That's not an overload. An overload, guys, is 10, 20, 30, maybe 100% more, like a 15, you're pulling 30. That's a ground fault, that's a overload. This one is a ground fault or a short circuit. Now look at, as the current, this is 150 at, for only 3 cycles. Only for 3 cycles, the current will go right here through these coils. The magnetic force, guys, created, look at this, the magnetic force created will push these contacts, this arm here, away from, this arm away, opening the contacts. Magnetic force. Aren't you guys amazed how, who thought about all these ideas? Don't you get excited about somebody somewhere come up with this idea? No? Am I the only one who's excited? Aren't they smart people to manipulate electricity to make it work for you? Create a magnetic force, like a coil, cylinder. It pushes the contact. The magnetic force that creates through the coil will push this arm, the solenoid arm, and it opens the contact. So that's your thermal. Luckily, most circuit breakers, this is how the, this is the magnetic. This is how they represent a magnetic circuit breaker. The circuit breaker on the wall, Joe, is both thermal and magnetic, the two components together. So that's what the name thermomagnetic circuit breaker. So here's your, this is the name thermomagnetic circuit breaker. Can I have a thumbs up, Chad? We fully understand that one. When you represent this one, guys, it looks something like this. Fat and fluffy. Okay, so this part here, this part is this part, and this part, the thermal part, is this. And you can see that? So this is a thermomagnetic. This is the thermal. I'm going to highlight the word thermal here. Where's the thermal? Thermal. And this one is the magnetic. Can you guys see it, how they curve? This is the current, inverse time current characteristic curve that you're going to be drawing with Chad in a second, later on next week. When you see a curve like this, the top is thermal. This little link here is the magnetic. Any comments? That's what the word thermomagnetic. So this part is for overload. This part here is for ground fault or short circuit. Ground fault or short circuit. Any comments, any questions about that, guys? If you understand this one, that might make you money one day. Because that's what, when we go next week, going to Bishat Kuli, guys, now I forgot his name, the engineer. They have one engineer specialized in doing this system. They're paying him tons of money to do this system analysis. And that chapter that you're looking at is one of the most important chapters for system analysis that we have. It really is. Very simple, easy to understand before you get into the curves when we go to SKM. Any comments, guys? Any questions about that? These two types? So that's your thermomagnetic. Circuit breakers, guys, have two ratings: trip rating and interrupting rating. So, for example, here's a 4,000 amp. This is my trip rating. My interrupting rating is 85,000 amp. Everybody knows what the trip rating. Trip rating is the largest amount of current that the conductor continuously can allow you to pull. Most of them continuously. The interrupting rating is the largest amount of current if you have a short circuit or a ground fault that the circuit breaker can handle before it explodes. So for short circuit, amount of current should cause the circuit breaker to trip open when it's exceeded. This one is for the full load, basically. Interrupting, the amount of current that you can interrupt. This one is for short circuit, ground fault. This one is for overload. Can you guys see that? When you see a 4,000 amp circuit breakers, I pull a 4,000 amp out of it, it would not trip. If I pull 5,000 out of it, I overloaded it, it will trip. If I have the same circuit breaker is rated interrupting 85, if I pull 85, if I have a short circuit up to 85, this circuit breaker will interrupt without turning into a big ball of fire. You put 86 on it, all hell break loose, and a big ball of fire might come out of the circuit breaker. Any comment, guys, about the interrupting rating and the trip rating for circuit breaker or fuses alike? That's my interrupting rating. Shunt trap and auxiliary switches. Most of circuit breakers, guys, bigger circuit breakers, they use them as contactors for control. So they have shunt trap. The term shunt trap, solenoid coil on the circuit breaker. You energize it, open the circuit breaker contacts by energizing the solenoid. You energize the solenoid, you put a voltage across it, and you open it. Typical example for this, guys, air handling unit circuit breaker to trip it if you have a fire alarm. If the fire alarm can send a signal to the circuit breaker of the air handling unit, say, hey, we have fire, stop moving the air through the building. How do they do that? They have a shunt trip on the circuit breaker. You order it with two wires coming out of it to control the circuit breaker. That's what a shunt trip is. Solenoid energized trips. Auxiliary contacts, the circuit breaker, guys, at least comes three-phase, comes with three contacts, right? These are three-pole circuit breakers. Then most of them come with auxiliary contacts on the side, normally closed or normally open, that you can wire to do certain things. So if you want, every time the circuit breaker is on, you want a light or a message to come to your iPhone, you have auxiliary contact, interface them with a communication device, and you get yourself, every time your air handling unit is running, it gets you a message in your iPhone. That's how important the auxiliary contacts are. Or it could be as simple as a light. Every time the air handling unit is running, there's a big red light or green light sitting there. Any comments, guys? Any questions? So illuminate indicator light or operator panel. So these are different applications for them. Any comment? Shunt trip, guys, by code, the data center that we have to trip all the air handling unit, the crack units have to trip if you have a fire alarm condition in the data center. So all of these PDUs carry that you sized, every single one of them have to have a shunt trip on it. It's the only way you can trip them. So if you have a fire alarm condition, there's a mushroom head button, emergency button like this one. The firefighters walk in, and the first thing you do is you push that button, and the data center shuts down all the air handling units and all the PDUs. So the smarter ones, the A guys, are going to write on their PDUs and crack units, say provide shunt trip. That's it. Shunt trip. That's a function, little function. Okay, here's how it looks like. Very simple, very easy, guys. This is all part of how this is all built into the circuit breaker. So you provide, here's for example, you can control, you can put 120 volt here, control circuit. This is my control circuit. If the temperature goes higher than a certain value, guys, you can close the thermostat and trip the circuit breaker because you don't want the machine to work if the temperature is high. That's one way of control. I could have a push button here, normally closed push button here. So if I see a fire and the air handling unit, I push that button here and it shuts down the air handling unit through the circuit breaker, through the circuit breakers. Any comment, any question about the shunt trip for circuit breakers? Shunt trip, Jeff, have you used shunt trip? Shunt trip with circuit breakers all the time, huh? Okay, auxiliary contact, guys. Every time, for example, if I want, this would be my red light, and this would be my green light. Oops, will be my green light. So I can have my green light. How am I going to do that? Okay, and then here's my comment. Come over here. Here's my 120 volt. Look at this. I can, here's a green light and a red light. If the circuit breaker is on, this will close. The green light will go on, and the red light will go off. Here's an auxiliary contact used. They give you green light, the circuit breaker is on, red light, the circuit breaker is off, or any other combination that you want to do. So these are the auxiliary contacts. Almost all power circuit breakers, guys, have auxiliary contacts. Okay, when it comes to, I'm going to give you a break in 5 minutes, guys. When it comes to air circuit breakers, the most common ones, there are three types of air circuit breakers. Type number 1 is molded case circuit breaker. This is type number 1. Type number 2 is low voltage power circuit breakers. And type number 3 is medium voltage circuit breakers. So molded case, you're looking at it, Jeff, right there in that panel. That's called molded case circuit breaker. They mold them all together, all the contacts, and nice black looking thing. Low voltage circuit breaker. Do you guys remember when Square D came here? And when you went to EMI, did you guys see big circuit breakers sitting there? They're big device, a foot by a foot by a foot. These are, they're not molded. You can look at the contacts, they draw them in. That's called power circuit breakers. Some of them are low voltage, some of them are medium voltage. 600 volt here, and this would be probably 5K, 15K, 25K. These are the medium voltage, or 35K, something like this. The only reason why they call them, guys, air circuit breakers, because the arc produced that contains hot heat. The arc is extinguished every time you open a circuit breaker. There's an arc, right? I'm a circuit breaker. I'm going to open a 4,000 amp. You open, you create a big arc. That arc is extinguished in the air. No oil, no vacuum. No oil, no vacuum. Any comments, guys? Breaking the air, insulating medium to break the air. The air is the insulation between the contacts. Here's contacts like this. Air is in between them, right? The minute I open it under the air. Who cares? When you open a huge amount of energy in the air, you ionize the air. The air becomes conductive. You create an arc. You need to get rid of that arc. If you arc in an oil, the oil will kill the arc. If you arc in vacuum, there is no air to ionize, so the arc will be eliminated. Who cares? Every time you open a circuit breaker, guys, over time, the arc will eat into the contacts, and after not a couple of times, after a certain amount of opening and closing, you have to go change the contacts. So because the arc is brutal. Okay, here's what we're talking about, guys. I have, I'm trying to interrupt here a 35,000 amp short circuit. Look at this. I have a short circuit, 35,000 amp, and the circuit breaker is interrupting it. And look what happened. You have all this arc. So Adam, what happened when you interrupt it, you ionize the air. The air becomes conductive. And then it arcs between these two contacts. You're trying to open them. As they open, they ionize the air, and they continue to conduct electricity for a while until that arc is extinguished. The smarter than Chad, they extinguish it with oil. They put it in oil, done. Or in vacuum, no air to ionize, or in air, and they put certain things here, the arc shoots here, that can minimize the effect of the arc. Can I have thumbs up, Chad? We fully understand every time the circuit breaker opens, there's a dangers of arc, right? Okay, so that's my arc circuit breaker. Okay, molded case circuit breakers, and again, I'll give you guys a break in a second here. Low voltage, they're 600 volt or less. Low current, typically 15 to, oh my God, 15 to, what is it, 1200, I think? Maybe 250, 2500. I think 15 amps to 2500 amp, you can get the molded case. Higher than that, it will be different. Protect small, you can use them for motors, lighting, or appliances. Splitter used on a higher voltage circuit. They use a splitter to extinguish the arc. Melt or isolate plates on top of the contacts, permit hot gases to escape, but lengthen the path of the arc. So here's how these guys work. I hope they have that picture of it. Well, I don't have that picture. There's a picture, guys, of it. I'll show you where they use. Where's that one here? They use these arcs to extinguish. There you go. If you guys don't mind me here, disregard this, Chad, because that's really a nice picture, I thought. Okay. We went through this, went through that. I'm going to go directly, guys, into contacts. Here you go. This is what they call a splitter, Jeff. They put all these, and these splitters will actually extend the arc and extinguish it better. So can you guys see that? These splitters split the air, the arc right in here, and help extinguish the arc. and move the arc away from the contacts so the contacts don't get damaged. Can you guys see that? The most important thing, your contacts, don't want contacts to get damaged. These are the splitters. This is how they look like. Somewhere in this, the splitters right here. Can you guys see them at the top? And the contacts, so it draws the arc away from the contacts. It draws the arc away from the contacts, and it cuts it into pieces. It eliminates the the arc. That's the most important thing of this. Okay, so that's my my low voltage circuit breakers. Any comments, guys? Any questions before I give you a? I need to give you a 5 minutes break because I really need to focus on that one. Any comments? Any questions? Cool. Should we have 5 minutes? Okay, let's take a 5 minutes, and then we'll move into the next part. Let me guys go over that one. So we talked about a little bit about molded case circuit breakers, low voltage circuit breakers, guys. The same thing. I'll show you a really nice picture. When it comes to circuit breakers, guys, the key point is how to interrupt the arc. So look at this marker that Chad, long time ago, they have for the air circuit breakers, they made two contacts, two sets of contacts. One for the main contact for the power, and the other one for the arc. So they draw the arc away from the contacts. And they also have air arc horns that draws the arc away from the arcing contacts into away from the arcing contacts. So that's away from the main contacts into, or away also from the arcing contacts. So let me show you an example of this one. Easier said than done. Let's go directly into this, my friends. Okay, so here's Jeff. Here's what an air circuit breaker looks like, right? Can you guys see that? Here's the contact, the main contact. Here's my main contact. Here's the power coming in, the power coming out, right? So here's my 4,000 amp coming in, coming out. If there's a short circuit, look what happened. This will open, this part will open, and also this part will open. These contacts is called the arcing contacts. So they draw the arc. All the arc is happening right here. And then they draw the arc all the way away from the main contacts. Believe it or not, this mechanism will save your circuit breakers from damage. So look how it, when it opens, it looks like this. Can you guys see that? This is what they call it air circuit breakers. Now here's my 4,000 amp coming in. Now done, interrupted. Can you guys see that? It's interrupted right in here. But also it interrupted right here. So the arc starts going in here, away from the contacts. Can you guys see there's no arc in the contacts whatsoever? It's all drawn away with arc horns, shooting him away into the splitter that split him and get rid of the arc. The key point, guys, when you interrupt the circuit is to get rid of the arc. If you don't have a way of getting rid of the arc and the energy and the heat, your circuit breaker will explode. So the heat and the energy will get out, dissipate to the outside and to the air and outside surrounding air, and the whole interruption is happening in the air. No oil, nothing. Can I have thumbs up, Chad? We fully understand how air power circuit breakers work. They have two contacts. Yes, no? Everybody's okay with that? Are we wasting your time or no? We're good? Okay. So that's your air circuit breaker. So draws the horn away. So we medium voltage circuit breaker, guys. Medium voltage operate at a much higher voltage, just like I said, 15K, 25K. Draw out coils. They have blowout coils that they use, connected in series with the arcing contacts. Current flows through them when the main contacts open. Buffer construct by attaching small piston operating lever. So let's look at the construction of that air circuit breakers. Typical tank oil. I don't know if we have a typical dead oil horn draw the arc. So they're bigger, guys. They have a couple of other mechanisms to get rid of the arc. So I don't want to go to the oil yet. So I don't know if I have a picture of it. So here's my arc. Okay, so this happened to be the this is typical tank of circuit breaker, arc. Okay, operated arcing actuator. Okay, so arcing contacts. I don't know if you guys can see. This is for the. I don't think this is my air. So you can see that here's the arcing contacts happening here. There's multiple things in this contact. The power coming in here. That's high voltage. Say we're bringing 200 amp at 15 kilovolt. The power coming in here and get interrupted right here. Can you guys see that? Get interrupted right here. So the main contacts is actually right. This is what connected together right here. And they have an arcing contacts, rod actuator rod, operator link. So that's either they do it in air or they do it they either do it in air or in oil. You fill it in air or they either air or oil circuit breakers. I can't emphasize more, guys. The idea is how are you going to get rid of this arc when you establish this arc? How are you going to get rid of this arc when you establish it? So let's jump into, so that's your air. Let's jump into the oil, guys. Full tank of dead tank oil. Here's my full tank or dead tank oil. Tank is grounded potential, blah blah. Low oil or oil pour type. Here's a couple of things, guys. They use double break type. Let's go directly into, and I don't claim to be expert in different types. Let's go directly into the picture that they use. The whole idea, guys, without making it too complicated here, plain oil. The idea is how, can you guys see the, Jeff, my friend, you can see how they bring the power here. Here's my power coming out. Here's my 200 amp at 15 kilo amp. Can you guys see that? And this goes down, connect here. And when it opens in the oil. So what does the oil do for a living? It extinguishes the arc. That's it. It's a means to extinguish the arc. Any comments, guys? Any questions? There's so many design of it. There's so many gauges when you go into the medium voltage. There's a lot of gauges, the pressure, temperature relief, and pressure relief for all these, because you don't want it to explode. You have oil. So the idea is it will minimize the arc, and immediately when it arcs, it's like you have water right at the top of the, or liquid right at the top of the arc. Any comments, any questions? That's your oil. You have an oil inside it. Does this have an oil? No. We rarely use this, if any, in medium voltage. I'm not aware of anything in the low voltage system that we use. Okay, typical vented type. There's another type, guys. They call it typical vented type, this guy. So when it interrupts, it vents. Same thing. I don't know if you can see it. It interrupts, all the energy is vented to the outside. Smoke, the whole smoke coming out, vented to the outside. All your smoke is coming out as you interrupt the power that's coming in and out. Any comments, any questions? Any comments, any questions? So that's typically outdoor. So you interrupt, all this energy that came out of interrupting it will be thrown out of the circuit breaker, out of your circuit breaker. Okay, so the last one, this guy, look how the smarter than Chad again continue to do it better. There's a vent. Can you guys see the vent where you vent all this energy out? And look at the contacts. To minimize the arc even more, Joe, they interrupt twice. Can you guys see they have two sets of contacts? They interrupt twice. Now what happens if you interrupt at two locations? You minimize the arc. It's all about controlling the arc. I can't imagine. When you have a short circuit condition, guys, I always describe it as, imagine you have semi-trailer running in front of you at 85 miles an hour, and you're behind it, and that semi came to a complete halt, and you are running at 85 right behind it. What happened to you? Right slam into the semi. That's the amount of energy that you interrupt when you have say 600 amp at 15 kV or 13.8 kV, and you're trying to interrupt it. That's the incident. Everybody understand that, guys? Yes, no? Okay, so that's another way to interrupt from two locations. Interrupt from two locations. The best of all worlds is the vacuum. There you go. The last one, my friends, as, I don't know if you can see that one, vacuum tubes. Did they show you vacuum tubes, guys, when you went to EMI? Aaron, my friend, did you guys see any vacuum tubes when you went to EMI? Any vacuum circuit breakers? The way these works, they have vacuum chamber, and they interrupt with cylinder. In a cylinder, they put the contacts right into a cylinder that have been the air have been evacuated from it. So when you interrupt, here's my 1000 amp. When you interrupt, if there is no air, Jeff, what's going to happen? Would you ever have an arc if you don't have any air? No, no arc if there's no air. That's the best of all worlds, right? When you get a vacuum circuit breaker expensive, your Cadillac type medium voltage circuit breakers. Again, these are medium voltage and high voltage circuit breakers. Medium voltage and high voltage circuit breakers. Okay, so that's what I want to show you guys about the circuit breakers before we get into. So these are the type of circuit breakers. Different categories and different tanks and double break. Vacuum circuit breaker, we talked about the vacuum. The notoriously famous thing about the vacuum, guys, is the air is removed from it. Contact inside sealed enclosure. Okay, the last thing I want to talk about, guys, is the overcurrent protection device, time current characteristic curve, and a couple of these curves that we're going to do, and coordination, localization. Okay, so I want to get rid of this and go to a couple of pictures and show you. Okay. The second thing, guys, on our agenda to do is time current characteristic curve. This is you guys going to be doing this one next week with SKM. We have a presentation of Mishad Cooley. They're going to giving you a curve like this. You must understand this curve. If you guys look at the top is the y-axis is the time. Can you guys see time in seconds? The x-axis is amps multiplied by 100. Everybody can see? Multiplied by 100. So that lit here is limit determined by the device interrupting rate, capacity, or the maximum available short circuit current. This here is the available short circuit current or the maximum interrupting capacity of your circuit breaker. So this is the limit is 35,000 amp. Cool. This is the instantaneous. This part is instantaneous. Means if you have a short circuit, the circuit breaker will trip within 1 cycle, 2 cycle, 3 cycles. Within 3 cycles, they get 1, 2, and the 3 cycle. Within 3 cycles, your circuit breaker is going to trip. Let me take you. So any comments, guys, any questions about how this works? We've done them. If you graduate from Dunwoody without understanding this, we cheated you. So the higher the current, the lower the amps. Let me take an example. Look at this right in here, guys. I'm going to take it right all the way down here. And from here to here is the clearing time. So if I have a short circuit and the short circuit is 25,000 amp, can you guys see it? 2,500 amp. It will take 13 seconds to clear it. It will take 13 seconds to clear it. To start, it could clear between 13 seconds to how many seconds here, guys? To 110 seconds. Because we're dealing with circuit breakers, guys, and mechanical equipment, we can't exactly predict when they're going to clear. So they give you between 23 and 110 seconds, this circuit breaker will clear. This circuit breaker will clear. Any comments, guys, how to read these circuit breakers? If I give you one on the final, would you read it?
What does that mean, clear?
You have a short circuit,
Yeah.
and the short circuit is 25,000. Clear open, we start the opening process at 23 seconds. So start opening, doesn't mean open instantaneously. 23, it took us between 23 or 110 seconds. We guarantee you, the manufacturer will guarantee you that it will open. But they don't know exactly because you're dealing with mechanics, right? Mechanics, depending on the situation, could open, but within that gap, the circuit breaker will trip. The circuit breaker will trip. Any comments, guys? Any questions?
It's possible for it to open right at the first one?
Yes. Yes. So that's where they call it minimum clearing time and maximum clearing time. Minimum, that's minimum needs this amount of time. Maximum, it could take up to 23, but somewhere in between, guaranteed that you'll open. Cool. Okay, instantaneous. Here's my instantaneous part, guys. That's my instantaneous part.
Here's my long time. This is my long time part. And this is long time pickup right in here. Long time pickup for 1,000 amp circuit breakers. Any comments, any questions? You can see the higher the amps, look at this one, amps. The higher the amps, the faster the circuit breaker will trip. The higher the amp, the faster the circuit breaker will trip. The faster the circuit breaker will trip. That's the inverse relationship between the amps and the circuit breakers. Any comments, guys? Any questions about how you read this curve? Anybody does not know how to read this curve? Look at the long time pickup, 1,000 amp. At 1,000 amp, it will trip. Can you guys see right in here? Because next week, you guys are going to be doing this one, not next week, the week after for us, for the project, the 4,000 amp. Everything, you're going to be looking at tons of curves like this. So you'll be able to understand them. Okay, so that's my curve. That's for a circuit breaker. If you look at next curve, this is adjustable instantaneous, guys. The same thing, except the instantaneous is adjusted. Can you guys see that this is a 30 cycle right here? This is a 30 cycle adjustment to the instantaneous. The one underneath it is 6 cycles. Can you guys see the 6 cycles and 30 cycles? 30 cycles is 0.5 of a second. 6 cycles, 6 divided by 60 is 1/10. 1/10 of a second. 1/10 of a second. 1/10 of a second. Adjustable. This is called adjustable instantaneous circuit breakers. Adjustable instantaneous circuit breakers. Why do I care about adjusting it? Because I need to coordinate them. Any comments, guys, about adjustable circuit breakers, instantaneous circuit breakers? Let me show you another example. This curve will tell you guys that when you have a short circuit condition, your circuit breaker have to trip within 3 cycles. Here's one cycle here. It's 0.016 of a second. Here's another cycle, right? Remember that here's a third cycle. Within 3 cycles, your circuit breaker will trip. If you have a current limiting fuse, guys, low peak current limiting fuses, they trip within a quarter of a cycle. So if you have a fuse, typically they trip within right in this area. Some fuses. Any comments, guys, tripping within 3 cycles for circuit breakers? Tripping within 3 cycles. Within. This means it might take a cycle, 2 or 3 to trip. Okay, here's a fuse. This is a current curve characteristic for a fuse. The same thing. The x-axis here is what? The x-axis, the y-axis is the time. X-axis is the amps multiplied by 10. So if you look at this one, guys, it says minimum melting time 25 seconds at 200 amp. This guy happened to be this baby is 120, so 10. It's 100 amp circuit breaker. 100 amp circuit breaker fuse. So it will melt if you put 200 across it. It will melt between 120 seconds, 25 seconds to 120 seconds. Can everybody look at this and understand that before I let it go? Everybody understand if you have a 200 amp pulled out of this fuse, it will open within 25 seconds to 120 seconds. We know it's going to open somewhere. From the point it starts melting to the point it's completely melted and open, it will clear time will go 120 to 25. So like 95 seconds, it will take it. Any comments, guys? Any questions? Anywhere, we guarantee that will trip. This leg here, guys, is the available short circuit right here, or the interrupting rating of the fuse, or the interrupting rating of the fuse. Any comment about the time current curve of a fuse? Inverse time current curve of fuse. Okay, we have ground faults. Here's a ground fault, guys, symbol of a ground fault. This ground fault, 2 of them, or one you can set it up at a delay of 0.0 seconds or 0.1 of a second. Can you guys see that, how we delay it? It's set at 1,000 amp with a delay of either 0.1 of a second or 0.5 of a second. Anybody knows why we delay these? Why do we delay the ground fault? To coordinate them. To coordinate them, you need to be able to delay them. So here's my ground fault. Here's coordination. All this will lead you guys to a very interesting overcurrent protection coordination with selectivity. I have two circuit breakers. Jeff, I have a main A and a B. And look, guys, can you guys see how they both overlapped? Do we have selectivity here? Can you guys see that this area here is overlapped? If you have overlap, what do you have? Miscoordination. Can you guys see this corner right here? This corner, these two circuit breakers are not fully coordinated. To make them fully coordinated, they cannot touch each other. They cannot touch each other. If I have a short circuit right now here, or a short circuit right now here, these two circuit breakers will raise to open, which means both of them will open, and that's no selectivity. Any comments? Can I have a thumbs up, Chad? We fully understand that these are not coordinated because they're touching each other. That's what I'm going to be doing next week with you when we coordinate these systems. Okay, so let's look at something that fully coordinated. This is beautifully fully coordinated system. So if you guys understand this one, you're cool. The first thing that we have here is we have a circuit breaker. This is a 20 amp circuit breaker C. Can you guys see that? Is fed from a 100 amp panel that's fed from 300 amp main. Can you guys see that? C, B, and A. These, and we are coordinating them. Can you guys see that the 100 amp, the 20 amp circuit breaker that feed the light is completely, utterly not touching any of the others? How can you tell that these are coordinated, guys? Are they touching each other in any way, shape, or form? No, they're fully coordinated. Can you guys see that? Everybody can see that they're fully coordinated. Can I have thumbs up at least so I know you guys? They're fully coordinated. No curve is touching anything else. So if you come all the way here, come back with this one, all the way to the other one, their complete coordination, right? With their curves, with their tolerance curve. And the last one is coming, that 15 amp circuit breaker coming all the way up, coming back, fully coordinated. Any comments, any questions? Any comments, guys? Any questions? Adam, my friend? We're good? Okay. Any comments about fully coordinated? Any comments, any questions? So when we do SKM, everybody knows how to do that? If I bring this on the final, would anybody be able to interpret it? Yeah? Okay. Cool. Brian? Okay. I will bring a few of these guys in the final and I ask you to interpret it. I'll give you a short circuit right in this area. And what's the interrupting rating? Which is but not hard. You go all the way up to here and cross and read it. What's the interrupting rating for the top one? Here and read it. What's the upper one? Here and read it. Very, very important to be able to read these. Okay? I want to emphasize this is a 20 amp. That's coordinating with 100 amp. That's coordinating with min of 300 amp. So that's my coordination. This one is coordination of a fuse and a circuit breakers. The same thing. If you guys, can you tell that these are fully coordinated? Are they touching each other? No, they're coordinated. That's really as simple as that. If they're not touching each other, starting from this point up and this point all the way up, they're not coordinating. This part is your instantaneous, and this part is your long time pickup and long time delay and so forth. That area. So this area will be for short circuit and ground fault. For the most part, this area will be for overload and sometimes also ground fault. Any comment, guys? Any question? Coordinating a fuse with a circuit breaker. They're fully coordinated. What was the rating of the fuse? I can't remember. Protection current limit fuses. Feeder overcurrent protection device, current limit fuse. Main coordination. 1600 amp circuit breaker. I can't remember what the fuse would be here. 80 times 10. 800. 800 and 1600 amp circuit breakers. Any comment, guys? Any questions about this coordination? Any comments? Any question? Fully coordinated. When I start coordinating with you guys, that's what we're going to be doing. The last thing I want to do, I believe it's the last thing, is coordinating the ground fault. This is very important, guys, because it has two coordination. Like hospitals, it has the overcurrent protection coordination here. That's my main coming back. And I have another fuse that coordinate with it. These two coordinate with each other. Can you guys see that? This is for overload, and then I have a ground fault. Here's my ground fault. Can you see the ground fault fully coordinated with the ground fault? So I have two circuit breakers. Each one of them have a ground fault. And now when you have a ground fault, Jeff, you coordinate the ground fault with the ground fault and the phase with the phase. What I call it, the phase with the phase. I have a 200 amp here and 1,000 amp coordinating. Look how they're set up. This guy's set at 1200 amp. This is a 400 amp. And look at the 0.5 and 0.1. This is what you're looking at. What happened in the hospital, guys? Fully coordinated ground fault and overcurrent protection devices. Fully coordinated ground fault and overcurrent protection devices. Any comments? Any questions? Everybody can see that they're fully coordinated, right? Because they're not touching each other. So that's what my ground fault is. Any comments, any questions? Anybody has any comments, any questions? That's all I have. If you guys understand this chapter, please read it carefully. This will help us when we move it to SKM and we do all the coordination and say, are they coordinated? Are they touching each other? Yes, they are not coordinated. Any comments, my friends? Any questions? Any comments, any questions? That's all what I want to show you from these curves. That's it. Thank you.